Hello everyone. Today I want to show you a really interesting question, in my opinion, regarding of this statement here. So this statement states that show that the sum for arctangent x and arctangent of 1 over x is a constant. In other words, this expression in particular is a constant value. Therefore, and I should put out that the value of x will be the positive of real numbers, just to be clear about it. But I believe that zero will not be included, yeah. But I don't believe zero is a positive number. It's I neither. But anyway, so and then hence obtain the sum. In other words, for x, for the positive value of real numbers of x, this particular expression will give us a constant value. So technically speaking, let's say we have a random number like 10. Okay, let me do a computation and then I'll show you proof on why it's a constant. But basically, we will obtain the value, right? And I suppose that 0 will not include because it's a reciprocal function doesn't take 0 in its domain. Therefore, we would say that x takes a positive real numbers of values. So how do we prove that that particular expression is a constant? Well, first let us define the expression. Then we could proceed with the proof. So let f of x be the function for the expression arctangent of x plus the arctangent of 1 over x. By the way, arctangent implies that it's a inverse trigonometry for the tangent. Arc is just basically another notation to indicate the inverse. Another notation that we could use is the power -1. It's not a power technically, it's just a notation to indicate the inverse. But sometimes I'm not very comfortable using that particular notations because sometimes I get confused with the reciprocal function. Therefore, I rather use the arctangent, so that will be a very straightforward solution that will not confuse a lot of people when I try to solve it. Anyway, okay, so first, before we start before we play around with the function, let us create a statement here regarding of the proof. So let's say I have a okay, let's say it's a constant, right? C is a constant, right? C is a constant. And now what happens when we take the first derivative of a constant function or a constant polynomial? What happens is that it will be zero. The derivative of a constant function will be zero. So basically, if we obtained the derivative of this particular function will be zero, the first derivative, then it implies that the function is a constant function. Then that's basically the proof. So it's very easy proof to show. That's why I am creating a video about it. It's very straightforward. So let us find the first derivative for it. So if you do not know, this is the derivative of an inverse function for trigonometry functions. And let me show you a proof first for the derivative. So let me create another function just to focus on inverse functions. So let's say y, but I'll be using a different notation to make it clearer. So let's say we have y is equal to the inverse tangent of x. And now when we inverse both sides, in other words, we will obtain tangent of y is equal to x. So this second line here, when we differentiate implicitly, let's say we differentiate both sides in respect of x, well, implicitly, because we treat y the same way as we treat x, but we put the notation dy dx to implement that. Is not the variable x we're dealing with. We are dealing with another variable, which is variable y. So let me write down here. Now, we know that the derivative of a tangent of y will be the second square of y. So the second square of y, then the outside of this function will be dy dx because we are differentiating implicitly, and we will be differentiating x will be 1. So from here, when we divide both sides with the second square of y, then we will obtain this particular expression. It will be, sorry, an equation which is second square of y. Now, I have no information, any variables that I'm currently using to substitute second square y, but we have the identities of trigonometry. So let me derive them first. And I'll be referring to the most famous one, which is the sine square of x plus this cosine square of x is equal to 1. And now what happens is that when I divide both sides with the cosine square of x, we will obtain tangent square x plus 1 is equal to 1 over cosine square x, which implies is second square x. So here it is. And now we see the similarities. So basically, for second square y, we can express it in another form, which is tangent square y plus 1. And when we refer back, we see that tangent y is x, therefore it will be 1 over x squared plus 1. So this works for all values of x. There's no restriction to it, so which is nice. Anyway, let's go back here. Let me put this on my right. Okay. Now, let's take the, okay, this is very, let me put this below. Alright, so now let's try and take the first derivative for this particular function. So as we know that for the inverse tangent of x, it will be 1 over x squared plus 1. And now for the second term, which is arctangent of 1 over x, we will be differentiate by using the chain rule. Okay, so here will be 1 over, let me rearrange this, 1 plus x squared. Here will be 1 plus 1 over x squared. And by using the chain rule, we have to differentiate 1 over x. And now, by using the power rule for 1 over x, we should obtain this particular result. Let me finish writing it down. Let me create let me x squared plus 1 over x. Then let me simplify this term. So here will be x squared over 1 plus x squared times with negative 1 over x squared. And now we could simplify this easily, and we are left with both terms. But we have to subtract both them because they are alike terms anyway. Therefore, from here we will obtain the result, which is 0. Now, previously we did discuss about what happens when we take the derivative of a constant function. It will be 0, meaning that the slope will be 0. Therefore, this implies that this particular expression or this particular sum is a constant. Now, the bonus question is that hence obtain the sum. So now, how do we obtain the sum? So I'll be stating that the x values will be the positive real numbers. Okay, therefore we could begin. Now, I'll be drawing a diagram, which is a right angle triangle, and I'll define this angle as my alpha, and this angle will be beta, and this will be my right angle triangle. And now, let's say I define for tangent of alpha will be x. Sorry, yes, tangent alpha will be x. And then basically, by using the acronym which is SOHCHA-TOA, you know that tangent of alpha will be TOA, which means the opposite and adjacent. So it will be TOA opposite of adjacent. So because it is x over 1. So now tangent of beta, what will be the result? It is similar to using TOA again. So, which implies that it's opposite and adjacent. We know that the opposite is 1, and then the adjacent will be 1 over x. X. Therefore, we will obtain 1 over x. And now, what happens if we inverse this particular equation here? Both equations, we inverse it. We obtain alpha is equal to the inverse which is arctangent of x, and for beta, we will obtain the arctangent of 1 over x. And we know that the sum for both of these angles are 90 degrees, or in radian, it will be pi over 2. So alpha plus beta both will be the result of pi over 2. And now this implies, by referring back to our equation here, so it will be arctangent of x plus the arctangent of 1 over x, 1 over x is equal to pi over 2. So it's shown. So the result sum will be pi over 2, okay, which means it's a constant. Then that is it lah, right? So I hope that this is very interesting. Sorry if my presentation isn't that appealing to some, but I'm hoping that it will be beneficial. And if there's any room of improvement, then do let me know, right? All right, thank you so much.